I would say, remember that these things are available and you don't have to write your own sorts, okay? In most cases, there will be sorts already available for you, and you can just do that, and it's quite uh, um, quite efficient and extremely convenient, and also bug-free. Because if you instead write your own version of, you know, of an algorithm like this, um, there could be bugs in this code. Who knows, right? You need to be very careful about making this decision that you're going to be using your own sort, as opposed to doing this sort, which also guarantees to be very efficient implementation of that sort. So, just an advice. Let's move on and see what else we need to talk about today. Okay, the original conversation started with the idea that sort by itself is very useful, because in many occasions, we would prefer to organize collections or sequences in sorted order. But in addition, it, of course, can benefit the binary search, right? So if we have this binary search algorithm, then we can essentially determine if we can find an element. And there is an example of this binary search where what happens here, that the internal implementation of the binary search is no longer a sequential search. Instead, the binary search requirement is that your collection is pre-sorted. So therefore, this is the appearance of our collection pre-sorted, right? So this is a list. And so what we do first, we divide the length of our list by 2, and therefore finding the index of the middle element. So of course, if you take the length of my list from 0 to 11, right? So we're basically in the middle, we have 2 elements, 5 and 6. So we choose 5 as a middle element. And then what we do, we compare, we say, determine whether 75 is in the list, right? So we say, okay, 39 versus 75, not the same. But we then assume that we have to look for 75 in the upper portion of this list. So we can completely disregard half of this list already. And then again, we'll be dividing this remaining part of the list by 2 and finding the middle element, making a comparison. Perhaps it will be 66. Then we'll be doing more and more searches, and eventually finding it. But here it will be still a few steps, but not as many as the sequential search, which will essentially be going from the beginning and doing comparisons of each element. So supposedly this is a better version of the search rather than sequential search. And again, there's an example here. If you're curious, then you can analyze what it does. And the outcome of any search can be found or not found. So this particular binary search returns an integer, which tells us that I found this element at this specific position. It returns back the position. If I didn't find anything, I will return -1. So to continue our example with collections, we can say collections. There is a binary search built in, right? So we have a built-in my list, and we can say let's look for bath, right? Let's look for this element, and what it returns back is the position, right? It does it. Position equal. Is that what it returns? Position. So then we can say system system out print my list get element at this position, right? And we can print both. We can say at position plus the position plus space and display what that element is, right? So not a bad approach, but remember that you cannot use binary search without the prior sort. Somehow you need to guarantee that the collection of elements is sorted. In here we're sorting it alphabetically by using collection sort and then using binary search. So if we execute this, it should at position 0, right? So let's space this a little bit and run it again, right? So at position 0 there is bad, right? So if we search for Joe, right? For Joe, if we change the value that we're searching for and run that, its position is 3. So 0, 1, 2, and 3. So it's working, right? So it's good to know. Now, there is also in the collections. Let me actually jump back to. Oh, where was I? Jump back to the collections documentation. In this set, there's also find